Hola chicos. ¿A ti te gusta mi camiseta nueva, Forged in Fire? Fue un regalo de mi mamá. Tengo mucha energía hoy. ¿Tienen ustedes mucha energía hoy también? ¿Estamos esperando los otros estudiantes? No hay personas que quieren hablar conmigo en español. Yo debo practicar mi español. Ok, vamos a empezar. All right. I just came from Spanish class, so I'm trying to practice my Spanish. So today I have a fairly straightforward lesson for you guys today, so I hope it'll be pretty easy. So we learned about the basics of waves last time. Here, let me focus this a little bit. So last time we talked about waves, all right, and introduced them for the first time. And today we are going to talk about wave superposition. Okay, wave superposition. And what wave superposition means is this is basically when two or more waves combine. Okay, so what you want to think about is if you've ever been on a boat before, which I hope you have been on a boat before at some point in your life, or if you've ever seen the water before, the water has a very complicated looking surface because it has all these waves. So we don't see, when we look at the surface of the water, we don't see the individual waves, okay? What we see is the superposition of many, many, many waves that have been created by various sources and are all combining to make the surface of the water that we see. Okay, so it's pretty rare that you just see one wave going through the water, right? It's a complicated looking surface, and we would say that that is a superposition of waves. Okay. So what happens is if you have two waves, okay, maybe wave 1 looks like this, and wave 2 looks like this, and these two waves are headed towards each other, okay, so we'll make them part of the same. So these two waves are headed towards each other. What happens when they combine is they are going to make an even bigger wave, okay? These two waves would make an even bigger wave. So in fact, what we would do is we would measure the height of this wave, and then we would measure the height of this wave, and when they overlap with each other, we would draw a wave that is the sum of these two heights. So, you know, it's going to be like this high. So when they combine, they make a wave that looks like this. All right. So that is called, so when this happens, when two waves combine to make a bigger wave, that is called constructive interference. So constructive interference means two waves or more. So this all can be applied to more than two waves. Two or more waves combine to make a bigger wave. Okay. And when I say bigger, it could be more bigger in the positive direction or bigger in the negative direction. So it can be bigger, you know, constructive interference means it's further from equilibrium, okay, from the equilibrium position of the medium. So that's constructive interference. So again, this also counts as constructive interference if you had two waves that were represented by troughs, and these two combine, they would make, that is still constructive interference, okay? It's also possible to have a situation where you have the crest of one wave, all right, meets the trough of another wave, okay? So we have a wave that's going up encounters a wave that's going down. And so when these two hit each other, you are going to, they basically will cancel each other out so that you have no wave. All right. And so this is called destructive, not deconstructive, but destructive interference of waves. So this is when waves combine okay, to make a smaller wave. All right. The thing about destructive interference is it can be complete or it can be partial. So this is an example of completely destructive interference. But what if we had a wave where two waves that have different sizes? So you have like an up wave, and then you have a small down wave, like that. When these two combine, because the amplitude of the smaller wave of this wave is smaller than the amplitude of the big wave, then they can't cancel each other out completely. And so basically what this one's effect would be just to reduce the size of the bigger wave. So that's called partially destructive interference. Okay? So we always want to think about, how do we perceive? Okay? How do we perceive constructive or destructive interference? So if we were talking about constructive interference of sound, it would be, so when two sound waves combine and they constructively interfere, that means that the amplitude grows. And so we perceive constructive interference as being louder. Okay? With light waves, we would perceive constructive interference of light waves as being brighter. That's essentially what a laser is. So a laser is a machine that produces a lot of light waves that constructively interfere. Okay, that's what a laser does. It makes a lot of light waves, but you could have a ton of light waves, but if they destructively interfere, you're not going to be able to see the light. So what a laser does is it times the production of the light. So you always have crests meeting other crests, so that you have bunches and bunches of waves constructively interfering, and so the brightness grows until it's, really bright. Believe it or not, I think it is a technology to have sound lasers where you create, I can't remember what it's called, because laser stands for light amplification by stimulated emission of radiation. So maybe they're called phasers or something, sound amplification by stimulated emission. But you can do the same thing with sound. Okay? And then destructive interference, obviously it would be quieter or dimmer. Okay? So one type of problem that you could encounter is you have a displacement versus time. Okay. So you have displacement in meters, or let's say displacement versus position. Okay. And I might show you the individual waves. Okay. So maybe the individual waves look like, maybe it looks like this. Here's wave 1, okay? And then wave 2 looks like this, okay? And let me put some numbers on the vertical axis. So this is wave 2. 2, 3, 4, 5, 6, 7, 8. So here's 5, 1, 2, 3, 4, 5. This is -5. here's 0. Okay? So, you know, if this were the shape of wave 2 and this were the shape of wave 1, and they combine, you are not going to see these two waves individually. What you would see is a combination, a superposition of those two waves. Okay? So what you would do is, it's just like if in your math class you have ever added f of x and g of x together. It's the exact same idea. So if you take wave 1 as like f of x, and you take wave 2 as g of x, all right, then what's going to happen, so wave 1 is f of x, wave 2 is g of x, then the superposition of the two waves, which is the wave that we would actually see, is called, is going to be f of x plus g of x. So what I like to do is I like to just pick a couple of points. So here at x equals 0, both waves have the value 0. So when I add them together, they give 0. Here, I can see wave 2 has a value of -1. Wave 1 has a value of +1. So +1 minus 1 is 0. Here, wave 2 has a value of about -2. And wave 1 has a value of about +3. So you have -2 plus 3, which equals 1. So I'll put a dot here at 1. Here I have this wave is at a value of like maybe -2.5. And this wave is at a value of about 4. So -2.5 plus 4 is about 1.5. Here, this wave has a value of about 4. This one has a value of about -2.5, so this is about 1.5 again. So I'm taking these two functions and adding them. Here I have wave 1 has a value of 1.5. Wave 2 has a value of -2.5. 1.5 minus 2.5 is -1. 0 and -3 or so. So those will combine to make -3. Here, and I don't have to do every marking here. Here I have both waves have the value -2.5, so they're going to combine to make -5. All right. Here I have one wave is -2, the other wave is -3, so they combine to make -5. Here one wave is -1, the other one's -3, so they combine to make -4, etc. Okay, so I build up some dots where I get the displacement of the superposed waves. Okay. And then I connect those with a nice smooth curve. Okay, so this is what the total wave will look like approximately. Okay. So what I can see is kind of in this region. See how both waves are negative in that region. So in this region, because both waves have the same sign, you can see that when they combined, they made a bigger dip. So in this area, we have some constructive interference going on. And in this area, we had one of the waves was positive and the other one was negative, so they were canceling each other out. So over on this side of the graph, we had destructive interference. Okay. So this process So this rule for combining waves this rule for combining waves is called the principle of superposition. All right. So that is the rule we were learning today. It's the principle of superposition. And so what it says is that the displacement of the total wave, or the superposed wave, or whatever you want to call it, is equal to the displacement of wave 1 plus the displacement of wave 2. Oops. So we add the two displacements. Now, the displacement of wave 1 depends on where you are, but it also depends on time, right? Because if you look at a wave, the wave is moving as time goes on, okay? So we would express that as saying displacement of wave 1 as a function of position, comma, time. So that means position and time. All right. So this is the displacement of wave 1 at location X at time t. All right. So let's just, because that notation is probably new for you. You usually, so this is called a function of two variables. All right. In math, in your math class, if you take more advanced math in college, you'll deal with lots of functions of two variables, or three variables, or five variables, or whatever. But typically, you just have f of x in high school. So let's talk about that just a little bit. Suppose that the displacement of wave 1 as a function of position and time is equal to 4 sine of 3x plus 2t. All right. So I could say, and by the way, for this lesson, we are going to have the calculator in Radians mode. Okay, I gotta even make sure I can do that on my calculator. Let me see if I can figure it out. Mode. Uh-oh. Let's see. How do I change it? Whatever. So what if I want to know what is the displacement of wave 1 So what is the displacement at x equals 1 meter and time t equals 4 seconds? So what I would do, okay, is I would plug in 1 for position. So I would have d1 equals 4 sine of 3 times 1 plus, and then I would plug in 4 for t, so I have 2 times 4. All right, so that's going to be 4 sine of 3 plus 8, sine of 11. That's not 11 degrees, that's 11 radians. Okay, so let's see, time 80. Oops. 11 times. And so this gives me right at about -4. Okay, so it actually was really close to -4 meters is the displacement. Okay, so in general, all of these are going to be functions of position and time. So that is called the principle of superposition, and that is the main formula that we are working with today. Let's do another example. So what if displacement of wave 1 as a function of position is equal to, let's say, 3 sine of 2x. Okay. And then what if d2 as a function of position is, oh my gosh, Hazel just let out a real stinker. D2 as a function of position is going to be negative cosine of 5x. So I have two positions as two displacements of waves as a function of position. Okay. And so I want to know, where do these waves combine so that they have completely destructive interference? Okay, so completely destructive interference means that the total wave d1 plus d2 has to equal 0. So that means that, and the fact that I'm asking for where means find the value of x. Okay, because these two waves are combining, just like in this example, like the total wave was right here. So I would say that they have completely destructive interference right at this location right here. Okay, because the waves are combining to make a 0 value for the total wave. So this is where there's completely destructive interference. So I add these two together. So I have 3 sine of 2x plus negative cosine of 5x. Okay, so now I'm going to add negative cosine of 5x to the other side. So I have cosine of 5x equals 3 sine of 2x. I meant to make this 2x. Oops. My bad. This should be 2x. This should be 2x. Okay, so now I'm going to divide both sides by cosine, and then I'm going to divide both sides by 3. So I have 1/3 equals sine of 2x divided by cosine of 2x. All right. and that is just tangent of 2x. So hopefully you guys know about doing the inverse tangent, also known as the arctangent. So I'll do the inverse tangent of both sides, and I get inverse tangent of 1/3 equals 2x, and then I'll divide both sides by 2. So that tells me that x equals 1/2 inverse tangent of 1/3. So let me work that out in my calculator. Okay, so I want to do inverse tangent of 1/3. Okay, times 0.5. And so what I get is these two waves will have destructive interference at x equals 0.16 meters. So that is the location. So they don't combine to cancel out everywhere. It's only at a specific location. Okay. So that's pretty much the content for today. I did want to show you one other thing, which is maybe you guys have seen the graph of, you've maybe graphed f of x. Have you ever graphed f of x minus 5? F of x, the quantity, f of the quantity x minus 5. If you have, you know from your math class that this graph will be shifted to the right by 5 units. Okay? So basically, if you have a wave, so maybe the displacement of the wave as a function of position and time is equal to sine of 2x minus t. All right? So what you can see here, all right, is that t is the shift. All right? So as time increases, as time goes on, the shift of the graph increases. All right? So this is depicting a wave this graph is depicting a wave that is moving to the right. So this is a traveling wave. Stop texting me during my lesson, Mrs. Lee. Okay. So let's go to Desmos here. So I'm going to pull up some Desmos. Because I want to show you how this works. Let's see. Come on, Desmos. All right. So we're going to look at a graph of displacement versus position. Okay, so there's the graph, and I'm going to put d of x equals 4 sine of, I don't know, let's say 0.5x. So there's a wave just by itself, displacement as a function of position. But what if I want to shift it? So if I want to shift this graph, I would put -3 or something like that. And that's going to shift it 3 units. It's going to shift the graph over to the right. But what if my shift depends on time? And so I add a slider. Okay. So you can see that as time elapses, the graph maintains its shape, but the shift amount changes. And so what we get is basically a movie of a traveling wave. Okay, so this is how the displacement of a traveling wave is represented as a function of time, which I think is pretty cool. And by changing this number here, you basically change the speed with which the wave shifts, right? Because a smaller amount of time results in a bigger shift, so you get a wave that's moving faster, okay? You could also change the sign of this. So now this wave is moving to the left. So you can change the direction and you can change the speed with which the wave goes from place to place. So anyways, that is how the displacement of waves is represented. It's usually a function of position and time. And when we have two individual waves, we have the displacement of wave 1 as a function of position and time. We have the function for wave 2 as the displacement of wave 2 as a function of position and time. And we add those two functions together, just like f of x plus g of x, to get the total wave size at a particular point at a particular moment. Okay, I hope that made sense. That's my lesson for today, and I will see you in the Zoom room.